We're going to now talk about a different type of function. So we're going to talk about ones that are defined by roots and then more specifically powers. So we're going to go through two different things within this section. We're going to talk about the root functions themselves and all of the properties, how to graph them, how to find the domain. And then we're also going to go through some of our exponent rules, refresh on those, because we're going to see them again in the future. So first and foremost, we're going to make a distinction between two different types of functions. So the very first one is what's called a power function. So you're going to see your variable to some power. This value of b is just a number. So we've worked with functions like this. We've worked with x to the first power, x to the second, x to the third. Those are some of our base functions. Also, x to the negative 1 is 1 over x. That's our rational function. So all of those are power functions. So again, just to give you some examples, this is like y equals x to the 7th, y equals x to the 0.9, y equals x to the negative 1, which is 1 over x. These are all power functions. What we're actually going to be concerned with is a very specific type of power. So if instead this value up here of b can be written as the fraction 1 over n, then it's called a root function. So if we have x to the 1 over n, it is the same thing as saying the nth root of x. So just to give you some examples, like if we have y equals x to the 1/2, this is the same thing as taking the square root of x. And when we have the square root, we just don't put a number in there. If we have y equals x to the 1/3, this is the same thing as the cube root of x, okay? So this is what we want to make a distinction of. We want to talk about these root functions, okay? So when we talk about the graphs of those, one of the most important things is finding the domain. All of them have the same basic shape. It just depends on whether the function is even or odd. So if we know the overall shape of our square root function and we can find the domain, we can figure out what the graph of this thing looks like and using our basic transformations. The biggest thing you have to remember is that when we're dealing with square roots, we can't take the square root of a negative number. So the square root of -1, remember, is a complex number. So it turns to the imaginary number I. So because of this, we have a very specific domain for even roots. It extends not to just square. We can't take the 4th root of a negative number, the 6th root of a negative number. So anytime we have an even root, we need what's underneath the radical to be greater than or equal to 0. So let's start with the graphs of both of these. We'll begin with an even root. So we'll start with the square root of x. When you plug in 0, square root of 0 is 0. When you plug in 1, square root of 1 is 1. And then remember, we can't plug in negative numbers. 0 is the very first one, and it has this overall shape to it. Every other even root is going to look very similar. It's just kind of a stretch or skewed version of this. So if we graph the 4th root of x, so there's a 4 in there. If you plug in 0, it's still 0. If you plug in 1, it's still 1. It just is a slightly skewed version of it. 6th root would look really similar. It just would be sharper and then go flatter, okay? So every even root is going to have that same shape, and then if you apply your transformations, you just move it left, right, up, down, and you reflect it. When we talk about odd roots, if you remember the graph of our cube root function, every odd root has the same shape. Goes through 0, 0, cube root of 1 is 1, cube root of -1 is -1, and it has that S shape to it. Okay. So our next odd root would be the 5th root of x, and it goes through exactly these same points, 0, 0, 1, 1, -1, -1, but it is just a condensed in function, okay? So odd roots have the S shape, even roots have that half parabola shape. For even roots, your domain is 0 to infinity. Your range is going to be the same thing. For an odd root, no issues with the domain, negative infinity to infinity, and the range is the same thing. And then you can also see both of these graphs are going to be increasing functions. So they're always climbing, climbing, climbing. So let's get some practice just with the domain, and then we'll do a graph of this first example, square root of 5x plus 4. So we want to find the domain, and we want to state it in interval notation. So I have to check what root this is because there's nothing inside there. You think of it as a square root. And with that being the case, we need to make sure whatever expression is underneath here is greater than or equal to 0. So we need the expression 5 plus 4x to be greater than or equal to 0. And if I can solve this inequality, that gives us the domain of this function. So these are much nicer. We just need to get x by itself. This gives us 4x is greater than or equal to negative 5. And then we divide both sides by 4. And since it's positive, it doesn't do anything. We get x is greater than or equal to negative 5 over 4. So if you need to make a number line, absolutely feel free. But this is our starting x value. We can equal it, and we can pick all values greater than it. So our domain in interval notation would be starting at negative 5/4 and go to positive infinity. Okay. For this next one, we have an odd root. So I just have a nice simple expression underneath it. There are no issues with odd roots. So this tells us our domain is from negative infinity to positive infinity. No problems. I can plug whatever I want into this expression and it will be defined for us. Okay. Our next one we're going to make a little complicated because we really have two functions within each other. We've got this 6 root, but we also don't have just an expression involving x. We have x squared underneath here. But again, because it's an even root, I'm concerned with this expression underneath. We need 81 minus x squared to be greater than or equal to 0. And unlike the last one, I can't just solve this for x because it's x squared. This is a quadratic inequality. So unfortunately, we are going to have to do interval testing. So this thing does factor really nicely. I can take this minus sign out, or I can go ahead and divide this by -1 just to make things cleaner. This would give us x squared minus 81, and then it switches the inequality to be less than or equal to 0. Again, you don't need to do that. If you're comfortable just factoring it like this, absolutely, but we're used to the x squared out front to factor. So now it's set up really nicely. We can indeed factor this. We need an x in the first spot to give us x squared. To get to minus 81, we need a -9 and a +9. And then we can check our outer and inner cancel each other out. So this gives us the correct factoring. So our important numbers for interval testing are going to be 9 and -9. So we go ahead and we set up our inequality. We have 3 intervals that we're going to need to test. So this is interval 1, interval 2, and interval 3. For the endpoints, because these ones will give us the 6 root of 0, we can equal them. So this is where we check that inequality sign. We've got the greater than or equal, so we are good. Okay. So moving on to our first interval, we can plug in -10 from there because that's a nice number. This will give us -10 squared minus 81 needs to be less than or equal to 0. This is 100 minus 81 is less than or equal to 0. And unfortunately, this gives us 19 is less than or equal to 0. So this interval is no good. And again, you can go back up here to test it out. If I try to take the 6th root of 81 minus negative 10 squared, it gives us 81 minus 100 under the 6th root, which is the 6th root of negative 19. So this does not work out for us. Okay. Moving on to interval 2, a number in between there is 0. 0 is always nice to plug in. So plugging that into our expression, this is 0 squared minus 81 needs to be less than or equal to 0, and that is negative 81 is less than or equal to 0. So this one does work, meaning we can plug everything in between these two values here. So again, if I plug 0 back in at the front, this gives us the 6th root of 81. It is a number that is making sense for us. Our third and final interval, we can pick positive 10 from there. And that would give us 10 squared minus 81 needs to be less than or equal to 0, which leaves us honestly with exactly what we had before. 19 is less than or equal to 0. So this interval is no good for us. Okay. So ultimately, just interval 2 is going to work out. So our domain is from negative 9 to 9, and we can equal these endpoints. So again, finding the domain is the most important part, because when it comes to graphing, if you can find the starting x value, what your domain has to be, yes, we know all these other transformations, the left, right, up, down, but anytime those compressions and stretches are in there, like in this one having a 4 attached to the x, it definitely makes it harder to get a good graph, but I know this is a square root function, so I know that its overall shape is going to look like this. We don't see any minus signs, so it's not reflecting in any way, shape, or form. And I have nothing on the outside, so I'm not moving this up or down. So ultimately, there are no reflections for this graph. And there's no vertical shifts. There's just been horizontal shifts and then stretches and compressions in that direction as well. But we already know the domain of this thing. We figured that out in the last example from part A. Our domain is negative 5/4 to infinity. Okay, so that means my starting x value here is negative 5/4. So there's no vertical shifts. We go ahead, we're going to start right here, and then I know it has that basic overall square root shape. So without a ton of work, I know this is what our graph is going to look like. We can also find our intercepts if we want to get a really decent picture. We also need to do that for finding part of this problem. But if we find the x-intercept, this is where our function is equal to 0. And this is kind of jumping the gun a little bit, because in the very next section, we're going to talk about solving radical equations. But we have a square root. To get rid of a square root, we square both sides. 0 squared is 0. So this is 0 equals 5 plus 4x. We go ahead and subtract the 5. And that gives us negative 5 is equal to 4x. And then we divide by 4. To give us our x-intercept is negative 5/4, which is exactly what we got from knowing the domain and knowing that there were no vertical shifts to this thing. Now finding our y-intercept is much nicer, because again, that just means we're going to plug in 0. So if we plug that into the function, it gives us the square root of 5 plus 4 times 0, which is the square root of 5. So this number is a little bit easier up here. This is the square root of 5. Okay. And again, typically when you're asked to find x and y intercepts, you want to write it as a coordinate pair. So this would be the point negative 5/4, 0, and this would be the point 0 root 5. Okay. So far we have the domain, we have the x-intercept, we have the y-intercept. We have not done the range, which I'll do right next to the domain. But because this thing hasn't been shifted, our range starts at 0 to infinity. I mean, it hasn't been shifted in the y direction. So the range has not been altered. Then we also need to find where this is increasing and where it is decreasing. And this thing is always increasing. It's always climbing, 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 climbing. So it is increasing from -5/4 to infinity, and it is never decreasing. Okay. And again, it shouldn't make a huge difference which one you put in. Typically, we like always using open parentheses for these, but if you don't, it's not the end of the world. All right, so now that we know a little bit more about these root functions, the thing that's more important for us is to actually find and work with exponents. So we want to talk about all of these exponent properties because these are going to come into play in one of our later units, which is where we deal with exponential functions and then logarithms as well. So the very first thing, if we have the same base and we have different exponents or potentially the same, if I'm multiplying two things of the same base, this means we add the exponents together. Because remember, all this is repeated multiplication. If I have x squared and I times it by x squared, remember x to the second means you're taking x times x. And then x to the second again means you're doing x times x. So you're really multiplying x 4 times. So we really just add these two exponents together. When we have division, it's the opposite. We take the numerator and we subtract the denominator because of cancellations. When we have an exponent to an exponent, this is where we get to multiply the two. So we would multiply p and q. If we have a negative exponent, you can always make it positive by switching its position. So here currently this is in the top of a fraction, so we would move it to the bottom to make it positive. For this next one, when the exponent's negative in the bottom, you move it to the top to make it positive. This one is just one we've already done. If you have x to the 1 over p, remember this means just take the pth root of x. Different variable, but still means the same thing. Okay. For this one, we have a fraction as an exponent, so p divided by q. This you can write as two different things. Because this is in the denominator, this means you're taking the qth root of x to the p. Or you could take the qth root first of x, and then the p is in the numerator, so it stays in that power position. So anything in the denominator of a fraction exponent is indicating what root you are taking. So let's try a couple examples with just numbers, and then we'll move on to manipulating variables. So we want to evaluate these expressions without a calculator. So meaning we want to get the final answer as just a straight number, no decimals, nothing like that. So when we're taking a cube root, remember that just means we're trying to find a number that multiplied by itself 3 times will give us 64. So 64, you can think of as 4 times 4 times 4. It is 4 to the 3rd power. So this cube and cube root undo each other. The cube root of 64 is 4. And then that minus sign just stays out front. Okay. For this next one, we have a fraction exponent. So you can go about this quite a few different ways. My gut instinct, because I have this negative exponent, is to turn it positive. So I would turn that positive by flipping it into the bottom. So it'd be 25 to the 3/2. And then here, to actually evaluate this, again, we could do one of two different things. This is the same thing as saying take the square root of 25 to the 3rd. But 25 to the 3rd is a very large number, and I definitely don't want to take the square root of that. So this is where it's going to make a little more sense to do the square root first, and then we cube it. Okay. So again, the thing in the denominator becomes the root that you take, and then the thing that's in the numerator stays the power. So it's always easier to take the square root first because that's really just 3 or 5 on the inside to the 3rd power. And then 5 cubed is 5 times 5 times 5, which ends up giving us 125. So this becomes the fraction 1 over 125. So I got 2 more examples. We want to rewrite these expressions with a single positive rational exponent just to, again, get more familiarized with these exponent properties. So I want to get y to a power. That's my whole goal. Or if one of these had x, it would be x to a power. So this is what we want, x to, or y to a number, y to a number. That's what I want to get for both of these. So you have a lot of different ways. It's your gut instinct as to what to do. You could say this is the square root of y times the square root of the square root of y, but that would be absolutely terrible to try to deal with first. So typically we like to work from the inside out when we're simplifying expressions. So I'm going to start with this thing on the inside because we've got a lot of square roots. So I'm going to start by turning this one square root into a power because we want y to a power. So the square root can simplify to y to the 1/2. And now we have something with the same base. So we need to add these exponents together. Since there's nothing here, this is the same thing as saying y to the first power. Okay. So this is really y to the 1 plus 1/2, which is the square root of y to the 3/2. Okay. So remember, y is the same thing as y to the first power, because y squared means y times y cubed means y times y times y. So y to the first means you multiply 1y as opposed to 2 or 3 in those other cases. All right. And now we're almost there. We still have a square root. So again, I'm going to do the same thing. I'm taking the square root of y to the 3/2. So we turn the square root into a power. And now because we have a power to a power, we go ahead and multiply these two together. So this gives us y to the 3/4 when you do 3/2 times a half. Okay. For this last one, we again have a couple different things. Maybe your gut tells you you've got that negative exponent and you want to flip it right away. Absolutely. Go right ahead and do that. So this is 1 over the cube root of y squared now to the positive 5th power, because again, we want positive exponents. And now here, I can rewrite that inside using our 1 property. So this cube root would turn into a 1/3 power. So the inside here is really y to the 2/3. So we're reversing that rule we used in the last example. And now we have a power to a power. So again, we multiply the 2, and this gives us y to the 10/3. And now we have y with a single positive rational exponent. Okay. Again, if you also don't like this step of turning the cube root of y squared immediately into that fraction, something else you could do, which will get you to the same spot, is maybe you don't recognize that, but you want to say this is y squared to the 1/3, and then we will raise it to the 5th. Okay. So maybe your gut just tells you, okay, I see a cube root, I make it a 1/3 power. And now here, we would multiply these two exponents, and it still lands you in exactly that step. We'd have y to the 2/3 to the 5th power. And then multiplying those gives us y to the 10/3. Okay. So if you need the extra steps, or that's what your brain naturally wants to do, absolutely go through that route. You have a lot of ways to do the same type of problem in these ones.